What is quantum entanglement? In fact, some of the most important features of quantum physics are the principle of superposition and quantum entanglement. The principle of superposition is given first at the beginning of every quantum mechanics course. Here I will introduce quantum entanglement and would like to explain it in the shortest way possible. Suppose you have a classic case. A person named Adrian, a person named Brian, and a third person named Charlie. Brian wants to travel to a faraway place, for example, to one of the stars. Adrian will stay on Earth. Charlie has a pair of gloves. The two gloves are connected by a feature, right and left. Charlie mixes the two gloves together and without looking, puts each glove in a box. The two boxes are the same. He gives Adrian one box and gives Brian the second box. When Brian arrives at his distant destination, he opens the box and sees, for example, that he has the right glove, so he immediately concludes that Adrian on the ground has the left glove. This is a very intuitive result that is well known and trivial in classical logic. We repeat the experiment, and this time Charlie has an isolated pair of electrons. One electron has a spin in the up or down state and the second electron has a spin in the up or down state. These two electrons are entangled, they have quantum correlation through the property of spin. This is only what is known. Therefore, the state of the two electrons together, and I emphasize the word together, is described as a single state vector. This is the basic idea of entanglement. This means that one cannot be described by a state vector separate from the other. Now without looking, Charlie gives both Adrian and Brian an electron. After Brian reaches his destination, he measures his electron, for example, along the x-axis. If he finds it spin up, the quantum state that was describing the entangled system collapses and Adrian's electron is spin down, assuming that Adrian also measures along the same x-axis. What is the difference between the classical and quantum examples? The difference between the first and second cases is profound, despite the apparent similarity. First, the two gloves were in a state that was already determined before Brian traveled, and before he looked at his glove. They are both classical systems. In other words, we know everything about the system, the pair of gloves, and we also know everything about the state of the components of that pair. We know the right glove from the left glove. This does not apply, however, to the two-electron system. Before the measurement, the system as a whole, the pair of electrons, was completely defined, as if the pair were a single particle, defined by a single state vector. But we did not know anything, and I stress, nothing at all, about the spin state of each of the two electrons individually, because the probability of up and down for each of the two electrons was 50% and 50%. In other words, the state of the system components was not known before the measurement. How the hell can we know everything about the system, yet we do not know anything about its components? This is the fundamental difference between quantum entanglement and classical correlation. Both classical and quantum systems have correlation within them, but quantum correlation, entanglement, is not self-evident. Fortunately, there is clear mathematics for it. Note, quantum entanglement may look like an information traveling faster than light. But this is wrong. Quantum entanglement and the collapse of the wave function that describes the entangled system cannot be used to transfer information between two places in the universe. It is not a transmission through space like light and cannot be used to transmit information from one place to another. This is because Brian may measure the spin on the x-axis, that is, in the measurement space of S sub x, and get spin up, but Adrian does not know on which axis Brian made the measurement, on x, on y, or on z. He might measure it, for example, on the y-axis, meaning in the S sub y measurement space, and he would get either spin up or spin down, and thus there is no information about the distant Brian system. Mathematically, the two measurements took place in two different mathematical spaces, one of which is S sub x, and the other is S sub y. These are two spaces, each of which also contains up and down basis states, and they are two spaces independent of each other according to the uncertainty principle. Information would only be transmitted if Brian measured his spin, say along the x-axis and got spin up, and then sent a message, by light or something, to Adrian on Earth that the measurement had been made along the x-axis. Only then will Brian be sure that Adrian will measure s sub x, and that he will definitely get spin down. Notice, then, that the speed of transferring information did not exceed the speed of light, but rather it was as fast as transferring the message from Brian to Adrian. However, information encryption can be done using quantum entanglement and hence under predefined protocols.